Okay, so let me first give a sort of outline of what I'm going to talk about. So, so I will be basically talking about a few topics in the theory of in non-Euclidean physics, which are not totally connected, but it's kind of interesting, good things to know about. And some of them are kind of related to what you will be hearing about in the next week's lectures. Okay, so the first problem is something called theorem. Okay, so this is a famous theorem on related to random walks. So I'll tell you what it's about. And the other thing that so the other thing that I'll talk about is basically about diffusion on one-dimensional lattice. On a one-dimensional Okay, so we have already studied diffusion on the mostly on free space, which means on the infinite line and in the infinite space. So this, so now what I'll talk about is diffusion on a finite lattice. Okay, so it's and so we'll study two problems. One is a single particle case, and then okay, so the single particle case, that's what mostly Sanjib has been talking about, and you can take, of course, n non-interacting particles. That's, I mean, if you know the one particle problem, and if they're non-interacting, then of course you also know the n particle problem, and then you can talk about n interacting particles. So the simplest interaction you can think of is that they just and two particles can't sit on top of each other. Okay, so this is called an exclusion process, and so I'll just introduce the problem. So this is, and you'll hear about it more in the next week's lectures. Okay, so this is so exclusion just means that two particles can't sit on top of each other. Okay, and while doing this, I'll basically introduce some concepts in non-Euclidean physics, things like master equations, W matrices, and steady state solutions, and maybe also relaxation to Okay, so when we are talking of diffusion on the open line, so there what we saw is that if you put some particles, like if you put some diffusing particles at some point, then they start spreading, right? And it spreads as a Gaussian. You saw you know the solution. So it's some Gaussian which keeps spreading forever, right? So it and because it's an infinite line, it will just keep spreading. It's a steady state in that sense. So now, but now once you're on a finite lattice, you can imagine if you have particles in a box, then they start diffusing, then of course eventually they will see the wall. So then it will eventually go to a state where it's a uniform distribution, right? So that's the steady state. So it will reach a steady state. And some questions you can ask is how does it reach the steady state and so on. So that's why finite lattice is important. And and while doing this, we'll learn various things about techniques in non-Euclidean physics. Okay. So the basic, yeah, goal will be to introduce you to some of the techniques and nomenclature in while dealing with non-Euclidean stochastic processes. Okay, so we'll start with Polier's theorem. Okay, yes. Okay, I just wanted to mention some sort of interesting thing about random walks that I just discovered. I mean, I was reading about yesterday. So the problem of random walks was first actually introduced also in the year 1905, okay, by someone called. Yes. So I mean, this was in 1905. This is the first time this problem was introduced, and this is the same year as Einstein was doing his theory of Brownian motion. Okay, so it's really interesting. And the problem he was studying was actually, I mean, something Sanjib mentioned. He was trying to understand, like, if you have a bunch of mosquitoes in in some region, then after time t, I mean, how far do they spread? Okay, so that's actually the problem he was trying to understand. Okay. So basically, he actually posed posed this problem in a paper in a comment in the journal Nature. So he just asked the question that I have a bunch of mosquitoes here, starting from some point, and what the mosquitoes, of course, do is they do a random walk, right? So they move some distance, and then they move like that, and so on. So each time step is a random, and you go in with some fixed length in a random direction. And you can make the length distribution also random, but this is what he considered. Okay. And then he asked if I take, if the mosquitoes take n steps, then where do the, after n steps, where are the mosquitoes? Okay. And then, so in the next issue of Nature, a solution of this problem was given by Rayleigh. And he actually solved it for if the number of steps is large. Okay, so you can't solve this problem exactly for any n, but you can do it for large n. And for large n, it's basically what Sanjib has been discussing about. It's a Gaussian distribution, and so this is the first time that this was obtained. So I thought this was just an interesting thing. Okay. Okay, so now what is Polya's problem? Okay, this I think again Sanjib kind of discussed yesterday in a particular setting, and I'll sort of discuss it in a different way. Okay, so the problem is you can think of the following problem. So supposing you, supposing there's a forest and there's a lion here. Okay. Okay, so there's a lion here, and then there's some sheep here. Okay, and so this is a huge forest, and we'll assume it's infinite. Okay, so now the lion it's not very clever. I mean it doesn't. And normally, of course, lions might be able to smell. I don't know if they do that. But what this lion does is it basically is doing a random walk. Okay, and then the question is, it does a random walk and then is hoping that it will eventually find the sheep, right? Okay, and the sheep, of course, they're moving very slowly, so we'll assume that it's kind of they're just sitting at one place. Okay, so the lion starts, so it's at some origin O, and the sheep are at some position on the plane X bar. Right? Okay, so so you can ask various questions now. I mean, from the point of view of the lion, the most interesting question is, of course, what's the probability that it will reach the sheep, right? So question number one. Okay, so okay, what would people guess? I mean, will it? I mean, is there some chance that it will never reach, or will it reach with probability 1? Huh? Okay, so in 2 dimension. I mean, this is a real world. I mean. Not real world, but anyway, approximately. I mean, so 2 dimension, right? It's moving on 2 dimensional world. Uh, yeah, I mean lines can't move up and down. Okay, so what is the answer in 2 dimension? 1. Okay, so that's okay. So many of you know. So the probability, okay, it does reach. I mean, so that's a good news for the lion. So the probability is 1. Okay. So question number 2 is, I mean, it might reach the lion, but what is the time it takes to reach the lion? Okay, I mean, so okay. So what is the guess for this? Okay, I mean, he knows all the answers. Okay, so so surprisingly, the answer is that okay, even though you will reach, the time on an average you'll take is infinite. Okay, so this is in 2 dimensions. It's 1. This is infinite. Of mean time, right? Yeah. Yeah. So you can of course change the problem that if it dies. Okay. Then question number 3 is so there's a time. I mean, so this is a random process, right? So every time, I mean, you can imagine different lines in different forests, and ask what is the. So each line might reach the ship in some time t. Okay. So the time t to reach the ship is a random variable, and you can ask what is the what is the probability it will reach the ship in time t. Okay. So so this is called the okay probability. Okay, so this is called the first passage time. So this time to reach the ship for the first time, that's called the first passage time, right? I mean, the name is clear. I mean, what it is, and this is called the distribution. Okay, so this quantity I'll denote it by P1. So line is at x, ship is at x bar T. Okay, so this is the probability density in time that the line reaches x bar starting from the origin for the first time between times t and t plus dt. The origin, what is the probability? Okay, so now just to make things more concrete, let's imagine also that the lion and sheep are on a lattice. Okay, I mean, you can just imagine that it goes trend in some way, and these are lattice points, right? So, and it moves between lattice points. Okay, so. Okay, so this is the origin, and I look at some lattice point x bar. So now it's a two-dimensional vector of integers. Okay, and the question is, what is the probability that I'll reach here after n time steps? Okay, so so you should be careful. I mean, when I look at continuous time, then this is a density in time. Okay, so it's distribution in time, and this is a probability density. Okay, but on the lattice, it's actually a probability. So, sorry, this is infinite lattice. You can do it for a finite lattice also. Okay, so now, so the question is that we are asking is P1 after time. Okay, so what is the probability that after n steps I am at x bar? Okay, so earlier what we have studied is this quantity P of x bar n, right? Which is what is the probability that if I take n steps, I am at x bar. Okay, so now are these two different? So what is the difference between two? Oh, so why is this not equal to this? So this gives me the probability. Okay, let's think of the lion. Okay, so now why is this not what we want? Right, yeah. So when we find this, okay, so what do we do? So we generate lots of paths, right? I mean, so, okay, so let's say this is you start from here. So in a particular realization, so this is where we want to. So in a particular realization, we might do something like this. So let's say we are taking n steps. So this is, okay, let's just make 4 steps. Okay, so supposing I ask what is the probability, so this is the origin. What is the probability that after 4 steps I am here? Okay, so if I take 4 steps, it could be, so this is step number 1, step number 2, step number 3, step number 4, right? So this is one realization in which at the end of 4 steps I'm here. Okay, so this is, so some other realization, of course, this is another 4-step walk which lands somewhere else. Now there are also steps, processes like it goes like this, like this, like this, and then comes here. Okay, this is another realization which also ends at the same point. Okay, now so when I calculate this quantity, I have to sum over all paths which after 4 steps have reached here, right? Now this also includes paths where at time 2, for example, this is already at this place, right? So I should not count those paths, right? So therefore, when I'm taking this, I also include paths which have already crossed x at some point. Okay, so therefore, this is not the right quantity, right? Because I mean, the lion, I mean, once it comes here, it won't just go and keep walking for a fixed amount of time and then come back. It will just stop. I mean, once it gets the sheep, it will just stop there, right? So what we want to ask is, you keep walking till you reach for the first time, and then you ask what is the time that I took. Okay, so this is okay. So I hope it's clear that these two quantities are therefore different. Okay, so now, so what I'll do in this lecture is basically try to compute all these quantities, and so you'll also learn some techniques. Okay, so let me briefly mention. So I think Sanjib already discussed this problem in 1 dimensions. So I think the problem that he discussed is the following. Basically, so it's on 1D, and let's say you, so you can imagine the ship is here, and this is the lion. So this is, let's say, some point z, and this is, so this is x equal to z, and this is x, this is the origin, x equal to 0. So this is the okay, and so the problem that you solved yesterday was what is the probability that starting from z, I reach, so there is an absorber at x equal to 0. Right, so you can imagine, see, the fact that once the walk ends immediately as soon as it comes at this point, right? So you can imagine there's an absorber there, and so it's and you basically, it's like solving the diffusion equation with some boundary conditions. Okay, so that's what you did yesterday. You put some absorbing boundary conditions at this point, and then you solve the diffusion equation, right? And what you got, I think, was P1 ZT. So this is in the continuous space and continuous time. So P1 ZT, is equal to Z by D. So this is what you did, right? This you did, right? Okay. So this is the usual probability distribution, and this is the first passage time distribution. Okay. Okay. So explicitly, this is Z by 4 pi D. Any questions? Okay, so now, so a few properties that I want to mention here is that, so this object is a distribution in time, right? It's not a distribution in Z. So PZ, this was a distribution in Z. So it was normalized to PZ, DZ, integral Z goes to minus infinity to infinity is 1. But this one is P1 is equal to 1. Okay, so that's something you should verify, which basically means that the probability that the walker will eventually visit this. So here the problem is you start your diffusion from here, and you ask what's the probability it will get absorbed between times t and t plus dt. So that is this, and if you integrate over all times, what's the probability it will ever get absorbed, right, at any time. And so it gets absorbed with probability 1, which means it will definitely visit this point. Okay, so the second thing is if you plot this function as a function of, so this is a function of time for any given z, then what will it look like? It will basically look like at very small t, it goes to 0 because of this factor. So it goes to 0 in some very sharp way, and then it's peaked at some value, and then at long times it decays with a t. So at times greater than z square by d, which is the diffusion time scale, this factor goes to 1. So it's just 1 by t to the power 3 by 2. Okay, so the long time decay is just 1 by t to the power 3 by 2. So this is a kind of important result to remember, that at long times the probability of returning in between times t to t plus dt goes as 1 by t to the power 3 by 2. Okay. So now because of this slow decay, and because it's power law decay, what you find is that if you take, so what is the mean time of getting absorbed here is basically dt. And so what is this? I mean, so you have to multiply by t and take this integral, right? Okay, huh? Okay, so the answer is, I mean, someone already said it should be what? This is the mean time of is infinity. Okay, so if something is infinity, it should be easy to prove. I mean, you don't have to do any complicated integral. So why is it infinite? Huh? T, yeah, so it's you basically I mean, so where does the divergence come from? Either it comes from small t or large t, right? Here at small t, there's no problem. I mean, it just goes to 0 in nice way. At large times, it's a slow decay, right? So if you multiply by t, you get 1 by t to the power half, and if you integrate that, it's t to the power half, which diverges, right? So therefore, the mean first passage time is infinite. And the infinite basically comes from the fact that it has a long power tail. Okay, so now let's just try to think about it physically. I mean, see, if naively, if you had guessed, you would have, if I asked you, like, if I put some diffusing particles here, I mean, how long does it get to get absorbed here? And the naive guess would have been what? You just look at how long it takes for me to diffuse, right? This distance. So the naive guess would have been just right. This is the typical, I mean, if I'm diffusing, this is the time scales for diffusion. right? So, but then why do you get infinite? Okay, so the reason is basically, I mean, when you start from here, I mean, a lot of walks actually, I mean, go a long way this in the wrong direction, and then they are coming back. Okay, and they give rise to this very long tail. Okay, so even though the distribution itself is peaked at the is actually peaked around z square by d. Okay, so if you look at the peak of the disease is around z square by d. This is the diffusion time scale. But because of these processes, rare processes, which I mean go, I mean have these long excursions, you have this slow decay, and that gives you. So if you have many particles, I mean most of the particles will actually come back in a finite time, but a few particles take such a long time that eventually your distribution is, I mean the mean time is infinite. Okay, so okay, so I mean, let me just go through the calculation by which you got arrived at this result. Okay, so so basically, the one of the simplest ways to get this result is basically you imagine that you are solving the basically again the diffuse. So the particle again satisfies the diffusion equation, right? So it's again the same equation, del p by del t equals to d. Okay, but now you have to solve it with a different boundary condition. So the boundary condition is that at x equal to 0, the probability distribution is vanishes at all times. So because I mean as soon as it arrives, the process ends, right? So it's like an absorbing boundary condition. Okay, and the initial condition is of course p of x at t equal to 0 is right. This is the initial condition. Okay, so now so this earlier we solved it on the free line where there are no boundaries, and we got some answer. And now with a boundary, you can easily convince yourself that this is the correct solution. Okay, so I will put a here for absorbing boundary conditions. So this is the solution of this equation with these boundary conditions. So I'll put a here. Okay, so now why is it a solution? Because okay, so now you can first of all you notice that each of this part, so this part itself is just starting from z. What is the probability of finding the particle anywhere, right? So this of course obviously satisfies the diffusion equation. Similarly, this also satisfies the diffusion equation, but with the initial conditions that it starts from x equal to minus z. So definitely both these parts satisfy this equation. Right, that's clear, I hope. Then the second point is you take the boundary conditions at x equal to 0, this cancels, so it's the boundary condition is satisfied. Okay, and then the initial conditions. Okay, so if you put t equal to 0, what do you get? The delta function, right? That's the initial. So you'll get delta x minus z and minus delta x plus z, right? Okay, so now, but this one you don't care about, right? Because it's on the, because you are actually confined to this. So this delta function occurs somewhere here, right? And you don't care about the, because you are just interested in this region. So you just ignore this. Okay. So this is like when you solve in electrostatics, you solve this by this method of images. So you have a conductor and you have a charge, and you want to find what is the solution. So then what you do is you put image charge, right? Of course, then the field out here will be completely different, but then you don't care. I mean, you're just interested in the field in this region, right? So it's a similar thing. So you don't care about this, and so this is the correct solution. Okay, so now, so what you have is you have a bunch of diffusing particles, and they are getting absorbed here, and this is the solution. Okay, so now if I supposing I take infinity. So what does this give me? What does it give me? Huh? Is it 1? Is it 1 or no? So what if, no, if you just think physically, what does it give? Sorry, say. No, it doesn't give. No, physically, what is? I mean, just saying words. What does it give? The probability of? No. See, because what is P? I mean, what is this quantity? This is just the probability that the particle is between x to x plus dx at time t, right? This is the usual probability distribution. So then, what does this integral give? The probability that it's anywhere in this region, right? I mean, I'm doing 0 to infinity. I mean, this region does not exist. It can't, there's nothing here. Okay, so 0 to infinity, I mean, the particle started from here. And if you do 0 to infinity, it just gives you the probability that there is still a particle in this region. Right? And why is it not 1? Because it's getting absorbed, right? So actually, if you, I mean, if you plot this distribution, what you'll find it looks something like this. Okay, so at t equal to 0, it starts from z, so it's a delta function out here. Then as you, for some time before it sees this wall, it's basically it will still look like a Gaussian. Okay, then at some point it sees the wall. I mean, so it keeps spreading, and once it sees the wall, I mean, here it has to be exactly 0. Okay, so it will be some. Now things start getting absorbed. Okay, so the area under the curve is of course the probability that under the curve. So that's initially it's 1, but now things are getting absorbed. So it keeps going down, and I guess okay, I'm not sure whether it moves this way or that way. Sanjib, do you know the peak? Does it move this way or that way? Okay, you have to work it out. Okay, I'm not sure whether the peak moves this way or that way. Okay, but basically if you look at the area under the curve, it keeps going down because things are getting absorbed. Right? And so it's good to just plot this function and see how it looks. But basically, because things are getting absorbed, it doesn't stay normalized. I mean, it just goes down. And this gives the probability that the particle is still inside here. Okay, so this is actually the survival probability, right? This is what I think Sanjib called S of t. This is the survival probability of the particle. Okay, so now what we want is what is the probability that it escapes between time t and t plus dt. Okay, so one way to do it would be just to take this function. I mean, if it survives till time t, and then what is the probability it survives? So if supposing I look at this quantity, survival at time t minus dt. Okay, so this is the probability that it has survived till time t, and this is the probability that it has survived till time t plus dt. So this difference must be the probability that it got absorbed between times t and t plus dt, right? So this must be equal to dt, right? So therefore, P1 ZT okay, so therefore you can find the, by doing this integral and taking a time derivative, you can find the probability that it hits between time t and t plus dt. Okay, now there's a second way of actually computing this object, and so let me just talk about that. This right, yeah, yeah. So I'm just going through so basically Sanjib discussed it in one day. I'm just repeating the thing, and then we'll come to higher dimensions. Right, so we are just redoing the calculation in one dimension. Okay, so I will eventually get this, so let me keep this. Okay, so there's a different way to calculate this. I mean, so it's nice to calculate things in different ways because they also give you better intuition of what I mean, where all this problem comes. Okay, so the other thing you can notice is that things are getting absorbed here. So there's a current here, right? So if you calculate the current here, that basically tells you per unit time how many particles are getting absorbed here, right? So therefore, what is the current at that point? What is the particle flux at that point? Huh? Del P del X into D. Right? So the current we know is given by this what Fick's law, right? I mean, so Fick's law is still valid. So D del P del X. But now I'm using this solution PAX, which is the solution of the diffusion equation with this boundary condition. So this is the current, and I want to evaluate it at this point. Right? And let's take minus j because this is the current going in that direction. I want the current going in this direction. Okay, so I'll take minus j and evaluate it at x equal to 0. Okay, so now what I'm saying is that this object is actually equal to right, because the particles which are getting absorbed, they're getting absorbed for the first time, right? Because I mean, after they're getting absorbed, they're not coming back. So therefore, this current must be equal to the first passage time. Okay, so now we can do this thing. So this is PAXT. So we have to take a derivative in x. So if you take a derivative in x, so what do you get? So there's a d times z okay, and then I have to set this x to 0. Okay, so if I do this, you can see that what you get is, so x is 0, so z plus z is 2z, so that's just, and d cancelled, so it's z by t e to the power. Okay, so this is what we had started with. Right? Okay, so this is a different way of deriving the same result. Okay, so you can also do this problem on a lattice, and let me just state what the answer is. So if you do it on a lattice, so this is of course the density. So this is P1, Z T. So if you do it on a lattice, then P1. So you get almost the same answer, where this P of Zn is this n factorial by Z minus n by 2 factorial and so on, right? So this is the on a lattice. And so here, so one question you can ask is, if I start from the origin, what is the probability I'll come back to the origin in after time n? Right. So does this work? So one of the questions I can ask is, if I start from the origin, what is the probability I'll return for the first time in time n? Okay, so you can see that if you put z equal to 0, then there's a problem, it doesn't work. So this value, for this result is true only for z not equal to 0. So for z equals, if you know this, you can figure out what's the result for z equal to 0. Okay, so this so I leave it as a problem. So basically, what you can do is you can think of it is in this way. So what is the question? I have a lattice, and I start from here, and okay, so let's imagine, okay, and so this is, let's say, time, and I keep walking, okay, and what is the probability I return in time n? Okay, in first time in n. Okay, so I can't take paths like this, right? Okay, so so to find this probability, what you can do is so the first step you take will of course be either here or this way, right? So now supposing I take the first step, so that of course occurs with probability half, right? And I'm here, and then I can say, starting from here, what is the probability that I'll come back to the origin in n minus 1 steps? So what is that? Okay, so starting from 1, what is the probability I'll hit the origin in time n minus 1? Right, so that you can just use this formula, right? So so you can just do this and see what the answer is. Okay, so this problem on the lattice, there's also a nice combinatorial way to solve this, which you can read in this review article by Chandrasekhar. So there's a very famous review article. Reviews of Modern Physics, 1942. It's called Stochastic Processes in Physics, Chemistry, and Astronomy. Okay, so it's one of the, I mean, it's a really great place to read about random walks, Brownian motion, and things like that. Sorry, 43 is it? Okay, 43. Okay, so I mean, the notation in the paper is kind of clumsy. I mean, I think that time maybe they didn't know vectors or all, probably, because they did never use divergence here. They just said del v1x, del v by del x plus del v y by del y plus, okay. So the notation is kind of cumbersome, but it's, I mean, there are a lot of very nice results, and there's a lot of physics and also very nice maths. Okay, so okay, so this is the result of on a lattice. Okay, so now let's. So are there any questions till here? Yeah. Yeah, I mean, that's most of the things will come back in that time, but there are some things which will take very long time, and they give rise to those tails. 1D. So now we'll see what happens in higher dimension. You had a question. No, but you can still ask the question. I mean, of course, if you say that if you start from the origin, you stay at the origin, then there's nothing. But you can imagine that you can leave, and then you ask what is the, and you can take the first step, and then ask what's the probability. So you start you start the process, right? And you ask, how long do I take to come back? I mean, I'm just starting from here. I keep walking randomly. How long do I take to come back? And that's a valid question. Yeah, I mean, observing boundary is just a technique to solve. I mean, but I can. Okay. Okay, so the other thing that maybe you should do is, so once you get this formula, like you have this exact formula, so just try, I mean, maybe, I mean, even in 1 dimensions, supposing you take a 2-step walk or a 4-step walk, right? and you enumerate all the walks, okay, and then ask what is the, what is this quantity. So you look at all the walks and find the number walks which have ended at a given point for the first time in n steps, okay. So just do it manually and see, so that is just to get a better feeling of the problem, okay, and see if it agrees with what you have here, right. I hope that the problem is clear. Okay, so now let's go to higher dimensions. If you have something like this, you start from here, and so you can put an absorber here, right? You can imagine that there's an absorbing surface here, and then do the same thing, right? So now you have to solve the diffusion equation in 2 dimensions, and then find what's the current here. Okay, so that's one way of doing this problem. Okay, so okay, so basically this, when you do random walks, you can either do this discrete approach or this continuum approach, right? So many things are easier in the continuous. So for example, if I ask what is the probability of this question, P of x at n. So in 1 dimension, on a lattice, you have an exact answer, right? So you know it's 1 by, so whatever, by 2 to the power n. Okay, so you have an exact answer for the probability after x n steps. What is the probability of being at x? Now, if you try to do the same on a 2-dimensional lattice, right? So can you do it? Okay, so has anyone tried to do this in 2 dimensions? Like the equivalent of this problem. So now again, you can ask the same thing, right? Okay, has anyone tried this, like on a 2-dimensional lattice? No, okay, so everyone stopped in 1 dimension. But in 2 dimensions also, actually, you can explicitly do this. It's a bit harder, but you can actually solve this problem, okay. So you'll get some slightly different, more complicated answer, but there's an explicit answer. But if you try to do it in any dimension higher than 2, then you can't do this exactly, okay. Because basically here, there are, when you derive this, you could go left or right, and the number of left steps and right steps is uniquely fixed by n and x, right? But on 2 dimension, you can go up, down, left, right, and n, and you have only 2 variables, so those are not uniquely fixed. So therefore, you have to sum over all possible combinations, so it becomes harder, right? Okay, so so therefore, to get an answer like this in higher dimensions on a discrete lattice is difficult. But if you look at the continuum version of this problem, so then you can always write the diffusion equation, right? This you can do in any dimension, and the solution of this is always is trivial in any dimension, right? So this question is easier to the continuum version is more easily tractable than the discrete version for this particular problem. Okay, so now for this first passage time, it turns out actually the lattice version is again easier, okay, to answer. And that's what Polya first studied, the lattice version of the problem. So we'll again go back to and stick to the lattice problem, okay, and not the continuous version. Okay, so. Okay, so what is the strategy? Okay, so okay, so for this discrete lattice problem, so what we know is that this P of xn satisfies a master sort of master equation, which is given by P Okay, so first I'll again do the 1D problem in on a lattice and then try to see how it's, so then the generalization is easy to the D dimensions, okay. Okay, so this is, so now, so this equation we know how to solve, right? How did we solve it? So the way we, okay, so let me first just tell you what the strategy is, okay. So the strategy is the following, I mean, is, so we'll use the, okay, so what is this? I mean, basically it's, if you have this quantity P of xn, so what I want to find is eventually, so we have these various things, right? P of xn and P1 xn. These are the two distributions we have discussed. Okay, so now what we want to do is we want to write a generating function for this. Okay, so generating function basically means P of maybe I can put a tilde here. Okay, so what is a generating function? It's basically your, so this is time, right? And I'm taking z to the power n and summing over all time, right? So it's basically, if you think of continuous time, it's like doing a Laplace transform. Okay, so if you had continuous time, what would I do? P of xt, I would do something like it. So this is the time variable, right? I'm summing over n, so I can integrate over t and put a s here, and integrate over all time. Right, and this is a Laplace transform of this variable. Okay, so this I would call P tilde. Yes. Okay, and this function has exactly the same information as this function, right? Because I can just take an inverse Laplace transform. So I mean, similarly, this thing which I call a generating function has the same information as this object P of xn. Okay, so. Okay, so okay, so the thing that I should mention is, see, this is like time and this is like space, okay, and in space also I can do a similar thing, right? And in fact, when you solve the diffusion equation, you took a Fourier transform, so you just took a Fourier transform in X, right? So, so usually, I mean, if there's time variable, you take a Laplace transform, and if there's a space variable, you take a Fourier transform, okay? So, I mean, that's, at least in many problems, that's kind of simpler. And once you take either so Fourier transform or a Laplace transform, the transform thing has the same information as the original variable. But it turns out that things become easier in the transform variables. Okay, so now here what, so this quantity of course we already know, right? And our objective is to find this object. Okay, so now what you can do is actually you can write a relation between P tilde and P1 tilde. Okay, So since so it's difficult to write a relation between these two, which also you can do, but then it's easier to manipulate the relation between these two guys. Okay. So therefore, once you have relation between these two, you can find this, and then you can invert this and find this. Okay. So that's the strategy. Okay. So now, so we'll try to explain this first for the 1D walk. Okay, so basically we want to compute this function p tilde of xz. Okay, so we have to basically, so let's try to do this by solving this equation. Okay, so how do you solve this equation? So if you remember this equation, we wrote pxt minus infinity. Okay, and then was there a 1 by 2? I think there was a 1 by 2 pi. Okay, so here I'm doing a transform in x variable, right, not t variable. So the way to is, so basically the idea is you expand p of xt in some basis, right? And on the open line, the basis is basically to the ikx, right? That's a complete set of functions and you can expand any function, right? So there's no problem in doing this, I can always do this. And then what you realize is that once you plug it in here, you get a nice equation for p tilde, okay? So we'll do the same thing here. So now what is the basis, right? We want to expand this p of xn. Okay, so now I mean the basis is not e to the power ikx, so the basis is actually, so it's let me just write it. Right, okay, so I mean, so what is this? This is just a Fourier series, right? So if you have a discrete space, then you have to do Fourier series, right? Because when you write e to the power I theta x, putting a wave vector greater than 2 pi doesn't make sense, right? Because you're on a lattice, so if you have it's greater than 2 pi, it's the same vector, right? So that's why you are doing like this, okay? So you do Fourier series instead of Fourier transform. Okay, so now you just, okay, so now we want to get an equation for p tilde theta, and just like we got an equation for p tilde kt. Okay, so what we'll do is basically multiply this equation by e to the power minus I theta x. Okay, so x, and here I multiply by e to the power minus I theta . Okay, so both sides of the equation I'm multiplying by e to the power minus I theta x, right? And here, because there's a x minus 1, I wrote as e to the power minus I theta x minus 1 times e to the power minus I theta. So it's still e to the power minus I theta x. So I'm multiplying by both sides by this object. Okay, and to get this, I have to sum over all x, right? So I sum over all x. And so then what does this give me? So this basically gives me p tilde theta at n plus 1. Is equal to, so now you can see that this will be, if since I'm summing over all x, this x minus 1 doesn't matter, right? So I can just put it x. So since I'm summing over all x, I still get p tilde theta n. So what I'll get is half Okay, I hope that's clear, right? Okay, so this is what? So this is equal to cos theta. Okay, so now so in the continuums case we had got something like dp tilde by dt, and we said that the solution is p tilde kt. Okay, so in the discrete case, so now once you have this equation, so what is the solution? So we want to a solution in time, right? So what is the solution of this? So it's a simple iteration equation, right? N plus 1 relates to n. So you can just keep iterating it, right? I mean, again, it's like solving this equation in some sense, but it's a discrete equation. So what is the solution? So the solution is p tilde theta n is what? Huh? To the power n. Okay. To the power n 0. Okay, so this is the solution, and then we just plug it in here. And so let's say we take initial conditions that at n equal to 0, it's at the origin, right? So therefore, this p tilde theta at 0. So what is this? If the particle at time 0 is at the origin, then what is the summation? Huh? So at n equal to 0, I'm saying this is delta x, right? It's at x equal to 0. So that means what? This summation is 1. Okay, at least I mean Arnav has to say because you are right in the big front. Okay, so this is therefore 1, right? So this is equal to 1. And there also I think we had got 1, right? I mean even in the continuum case. So this is the solution, and now you just plug it in here. Okay, so this is P of xn. So now, so this is again a homework. If you, can we do this integral? Okay, this is very easy integral. Okay, so you just put cos theta is e to the power I theta plus e to the power minus I theta by 2, expand the thing, and then you will see that only one term in the expansion survives. And what will that give you? So because this you already know the answer, right? It should give you that. So what is the answer? It's basically this n factorial by whatever, n minus what factorial, right? So it should, so just make sure that if you do the integral, you get that answer. So that's contained in this. Okay, you can also get the Gaussian by doing some expansions and so on. Like you expand cos theta as 1 minus theta square by 2, and then for large n, you'll basically you can replace this by minus infinity to infinity, and you will get the Gaussian. So all those limits also you can get from this answer, but we'll just keep it in this form. And now let's find the generating function. Right. So the good thing is now it's easy to find the generating function. Okay, so p tilde. Okay, so this part actually we solved by taking a Fourier transform in x, and now we are taking kind of a Laplace transform in z, right? So we'll take this, and so what is the definition of this generating function? So this is sum over okay, so if you multiply this by z to the power n, and sum over n equal to 0 to infinity, so what do you get? 1 over this, right? So this is equal to 1 by 2 pi x1. So this object is actually the uh, okay, so you can imagine, supposing you have a infinite lattice. So right now we are doing everything on the infinite lattice, right? So you have an infinite lattice, and you start from the origin, and this is some point x. So you keep walking, right, forever. And you ask, if I'm sitting here, how many times does this walker come to this site? Okay, so the answer is actually this object. Okay, so now let me just explain why that is. Okay, so now what is P of xn? Okay, so I take a n-step walk, and what is the probability of finding x? Okay, so this is, you can imagine that, so if you have an n-step walk, I mean, how many possible different walks are there? Huh? How many different realizations can be there? N-step walk. If you have two-step walk, I mean, how many different possible realizations can be there? 4, right? And if I have n step, 2 to the power n. So 2 to the power n different realizations. Now supposing I do all those 2 to the power n realizations, and then what is P of xn is 1 by 2 to the power n, and then I sum over all these different realizations, and in each realization I'll count how many times at the end of the walk the walker is at position x, right? That's the definition of this probability. So I'll put an indicator function here. Okay, so this is called so let's say in any realization of the walk is given by, let's say, x. So any is let's say x1, x2, xn. So this is a given realization of the walk. First step it's at x1, second step it's x2, x, and last step, n step, it's xn. Okay, so I will have different 2 to the power n such realizations. Each will be some different sequence, right? And I look at at the end of the walk, the position should be at x. I count those walks, right? Out of all those walks, I just count the walks which have ended at this position x. So I just put xn comma x. So this is an indicator function. It's just a delta function. If xn equal to x, it's 1. Otherwise, it's 0. Right. So I just sum over all these realizations, and I look for the realizations for which the walk has ended at x. Okay. So this is P of xn. Now, supposing I sum this over so this is the number of steps, and I'm changing this number of steps from 1 to capital N. Okay. So now I take this in and put it in here. Okay. So now again I have so many realizations of walks, and for each walk, so what is this quantity? So this is the number of steps, right? So this is step number 1, step number 2, and every time I am counting this. So what will this quantity give me? Huh? No. See, there's a, no, this is a delta x. I mean, these are all the, if at any step I am at x, right, then this is 1. So in a given realization, so see, supposing this is just one realization, okay. In one realization I am counting this object. See, you have to think physically. In a given realization, supposing just one realization, right? I am taking okay, so supposing my walk is this in 1D, right? So I'm walking like this, like this, like this, like this, like this, like this. Okay, so this is origin, and supposing I put x equal to 1. Okay, so x equal to 1. and this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So the number of steps is 9. Okay, so and what is this? So now what is this object? For this serialization, what is this object? So I at every time step I look at xn. What is the position of the walker? If it is at 1, I put a 1, right? Now at this step it's 0, right? Now it's come back, so again I put a 1. Again it leaves, and then again at the end it has come back. So what does this give? If I sum this, it's the number of times it has visited this point in a given realization, right? So in each realization, this object gives me the number of times I have visited a given point x. Okay, and then I sum over all realizations and divide by the total number of realizations. So therefore, that gives me the average number of visits to this site x, right? Okay, so this is if I take n number of steps, and then I can set this n to infinity, and then this object is just p tilde x1, right? Because p tilde x1 was px n z to the power n infinity. So if I put so this one is I can put 0. D0 doesn't matter because okay. So here if I put z equal to 1, this is not there. So then it's basically this object, right? So so therefore, what we have shown is that this is equal to the mean number of visits to the to the site x. Okay, any questions? P1 tilde x1. What is this object? I mean, physically, what is it? Huh? No, why you want? Huh? So it's the, but no, physically what is it? It could be 1, but what is it physically? It's a probability that at some time it reaches here, right? So it's the probability of getting absorbed, right? At so this one gives the probability that it arrives at time n. Then for probability of arriving in time 2, probability of adding at time 3, you add all the probabilities, is probability you arrive at some time at that site, right? So that now we want to see whether it's 1 or not. That's the question, right? So this is the probability of site x. Okay, so now we will relate this object to this object. Okay, so that's what. So in general, you can relate p1 xz to pxz, but let's first relate just this to this. Okay, so if I ask what's the okay, so let's see p of okay, so let's first look at just x equal to 0. 0, 1. This is okay. This object we said is the mean number of times the origin is visited, right? By starting from origin, what is the mean number of visits to the origin? Okay, so now what is the mean number of visits to the origin? P1 0 1. So this is equal to. Let me just write 1. Okay, so this is, it's possible that the walker visits the origin after just one step, uh, and sorry, what is this one? Right, yeah. So the mean number of visits to the origin is probability that it comes back after one step and then never comes back. Okay, so I want to find what's the mean number of visits to the origin. Okay, so it's possible that it comes back once and then never comes back. Okay, or it comes back, let's say, twice, and then it never comes back. Right. Okay, so let me just write and then let's say 2 probability. Okay, so let's make sense of this. Okay, so what is this? So this is probability. It comes. It's the mean number of times it comes to this. So this is probability it comes back in one and then never comes back. This is what is the probability it comes to the origin for the first time in one step and sorry, what is this? Mm. Okay, right, yeah. So what is this? Okay, so this is, it starts from here. Okay, so it's already at the origin, right? So there's therefore one, it's already there. And then it never comes back, right? So that's, I hope that's clear. Okay, then what it can do is so this is already one, so it can come back once, right? So what is the, and then it never comes back. So then there are two visits. Okay, so there's a probability of returning once and then it never comes back. Okay, so there's always this factor is constant, and this is the probability it comes back. So once it comes back it comes back for the first time again. Okay, so this of course it need not be just after one step. It could be something like like it goes takes many steps, and but comes back exactly once and then never comes back. Okay, so you can you look at all processes. So there are some processes where it comes back. Where it starts from and never comes back. Right? There are lots of processes like that. Right? So this is you just the number of visits is just one, and then the probability of not coming back. Now for this, what is the probability that it started, it came back once, so that is this object, and then it never came back, right? So this will include all various, processes that can lead to this thing. And similarly, if you can ask, it came back thrice, like it was already there, then it came back twice more, so that's why p1 tilde square, and then it never came back, right? So there are all these different processes. Okay, so therefore you sum up over all these things, and so if you look at this series, it's basically equal to 1 minus p1 tilde 0 1. So that's common to all the things, and then you have 1 plus 2 p1 tilde plus 3 p1 tilde square plus so on. Okay, so now this series you can sum. I'll just give you the answer. So if you sum this series, it's equal to 1 by 1 minus p1 tilde 0 1 plus 2 p1 tilde square plus 1. Okay, so now this series you can sum. I'll just give you the answer. So if you sum this series, it's equal to 1 by 1 minus p1 tilde 0 1 plus 2 p1 tilde square plus 1. Okay, so now this series you can sum. I'll just give you the answer. So if you sum this series, it's equal to 1 by 1 minus p1 tilde 0, 1. Okay, so now we are almost there. So this is P1, 0, 1 equals to this. And so if you invert this, so you invert means so you get 1 minus P1 tilde 0, 1 is equal to 1 by P1, 0, 1. And so therefore P1 tilde 0, 1 is 1 minus that. Okay, so that's this result. Okay, so let me just say what we are trying to get. So this is the probability of return, right? And we have what we have managed to do is we have managed it to relate it to the this other generating function which has the physical yeah. This is tilde. Thanks. Yeah. No. Oh, there's a tilde, right? Yeah. Where here? No, this is tilde. Okay, thanks. Okay, right. Okay, so this is the generating function for the usual distribution, which we have a formula right here, right? So what which has the physical interpretation of mean number of visits per site at the origin. Okay, so now we have an expression for this, right? So we'll put x equal to 0 here, and z equal to 1. So this becomes 1. Okay, so now what is this? Huh? Infinity. So if it's infinity, it's always easy to do integrals. Okay, so it's infinity because there's a divergence at small theta, right? So if you add small theta, this is theta square, so 1 by theta square, and that diverges, right? So this is infinite. Okay, so therefore now you can you get 1 minus 1 by infinity, so therefore this is 1. Okay, so therefore the probability of returning is 1 in on the one-dimensional lattice. Okay, so now the good thing is that we can, I mean, it's very easy to generalize this to any dimensions. And so let me just quickly outline the steps. So this just becomes a vector, right? So we have all this, these are now just vectors or with integer arguments. And we want to, first we want to get a solution for this object, find this object, and then relate these two objects, okay? So now this relation that I wrote out here, this is quite general, right? This will work in any dimension. So okay, so we therefore, okay, so let me, I think this this is kind of not a good notation, okay? So I'll just change my notation a bit. Let's call this what? Maybe G. I mean, G, usually Green's functions are called G, right? So G. Generating function, okay. Let's say, so okay, so let's call this G, and this is G1. Okay, and the result we obtained was G1 okay, so now this is origin, I'll just call it, this is, so this result of course is a very general argument, right? This is always valid. I mean, I didn't use one dimension anywhere here. So this is true. Okay, so now basically we have to somehow find this and then calculate this and then show is it 1 or is it less than 1, okay, in various dimensions. So again, how do you solve this equation? P x bar should be able to finish. So now it's a general d-dimensional lattice. So you have to sum over, so you have many directions. So let's just call any direction E. So there are unit vectors in d dimensions, and I have to sum over all the directions. So S equal to 1 to d, and P of plus E. Right, so basically the point is that I can come from any of this, in 2 dimensions I can come from 4 directions, and in d dimensions I can come from 2d directions. Huh? Okay, so now again I will basically use some basis. So I will expand x bar n as, so what did I do there? 1 by 2 pi. Right, so this x variable I am taking a Fourier transform in d variables. So now theta is some vector, theta 1, theta 2, theta d. So it's just a straightforward generalization, and the Fourier inverse is of course given by okay. So then what do? We just basically multiply again this by e to the power minus I theta bar dot x bar, and do the same business out here, and then obviously what you'll get is tilde uh, is equal to, so there's a 1 by d, and from here, I mean, so when you write this as e to the power I minus I into e to the power right, so this is what you write, and what is this e to the power I theta e to the power I theta bar dot es hat. So basically this will pick out the theta in the in a given direction, right? So this will be just e to the power I theta s. Right. Okay. So therefore, if you do this, what you will get is 1 by d sum over cos theta s. So these are the d dimensions, s equal to 1 to d p tilde n, and again you just iterate n times, and you get here that this is just 1, right? So this is equal to 1. Okay, so now so if you just do this, so you plug this solution in here, and what you'll get is p tilde. This is not tilde yet. I guess you can basically see what's going to happen now. 1 by 2 pi d. Okay. So I'll just write it here, right? I'll just put this in here. Okay, so that's the general formula for the generating function. Now we want this special case, put x bar as the origin, right? So if we put And so let's do this in 2 dimensions. So 0 z, but what you can see immediately is that this is again infinity. Okay, so why is it?